Now we'll go over problem solving related to the concepts from Chapter 11. First, we'll look at hybrid orbitals and valence bond theory. This table is a quick summary of what we learned about hybrid orbitals. Across the bottom, we see the various electron groups for VSEPR representations. And then above that, we see the corresponding atomic orbitals that are mixed, the hybrid orbitals and their number, and then the unhybrid orbitals that remain. And we'll see that these play an important role in bonding as well. So our sequence that we have now, we know how to take a molecular formula from a name, produce a Lewis structure, use that to determine the electron group arrangement from which we can derive a shape, and then from the electron group arrangement we derive hybrid orbitals, and based on the hybrid orbitals we develop a valence bond representation for a molecule. We're going to go through and use all the molecules we've used thus far. So we took a series of molecules, we took the formula to produce a Lewis dot structure, then we went and took the Lewis dot structure and did a VSEPR representation, and now we'll take that VSEPR representation and develop a hybrid orbital representation for that system, and then finally describe the valence bonding that is involved. So for oxygen difluoride, the central oxygen atom is 4 electron groups around the central atom, and it is a tetrahedral electron group arrangement. That tells us that it is an sp3 hybridized system. There are 4 electron groups, we need 4 orbitals, and there are 4 sp3 hybridized orbitals. This is our pictorial representation for the oxygen atom. It's a 2s2, 2p4, and we mix all 4 of these orbitals to produce 4 sp3 orbitals. And there are 6 electrons that need to go in there. So we have 4 of the electrons are paired up into 2 pairs, and then 2 of the electrons remain unpaired. The 2 half-filled sp3 orbitals participate in a sigma bond to the half-filled 2p orbital for each of the fluorine atoms. And then the lone pairs are represented as the filled sp3 hybrid orbitals. Next we have carbonic acid, and there are 2 central atoms here. We'll focus on the carbon initially. The carbon central atom has a trigonal planar electron group arrangement. There are 3 electron groups, therefore there need to be 3 hybrid orbitals, so it is an sp2 hybridized system. There are 3 sp2 hybridized orbitals. We can show the carbon atom thusly. We have a 2s2, 2p2 electron configuration for the free atom. We mix our orbitals in this system, then we have 3 sp2 hybridized orbitals, and then 1 unhybridized 2p orbital. Now notice that we have electrons in all the orbitals. We don't follow the off-bow filling scheme as we would with molecular orbital theory later on. That's because this is a different representation. The 3 half-filled sp2 orbitals participate in sigma bonds to the 3 oxygen atoms. 2 of those oxygen atoms, they're singly bonded, and 1 is doubly bonded. So the first bond is the sigma bond. The half-filled 2p orbital on the carbon atom participates in the pi bond with the oxygen, that is the second bond in the doubly bonded system. So the 3 sp2 hybridized orbitals give us the first sigma bond all the way around, and then the double bond with oxygen comes about from the unhybridized 2p atomic orbital, interacting with an oxygen p orbital. Next, we can look at the oxygen atoms on this system. The oxygen atoms have 4 electron groups, indicating a tetrahedral electron group arrangement. For 4 electron groups, that tells us we have to have 4 sp3 hybridized orbitals. We can represent them thusly. We take our 2s2, 2p4 electron configuration, and we end up with 4 sp3 orbitals, 2 of which are filled and 2 of which are half filled. Our valence bond representation then, the 2 half-filled sp3 orbitals participate in sigma bonding to the carbon and then to the hydrogen. So the oxygen has 1 hydrogen bond and 1 carbon bond. And that comes about from the interaction with the sp3. So for oxygen, the oxygen-hydrogen bond would be an sp3 with a 1s on the hydrogen. And then the oxygen to carbon would be the sp3 on the oxygen with the sp2 on the carbon. Next, we have nitroxyl. Nitroxyl has a central nitrogen atom with 3 electron groups. Therefore, it is a trigonal planar. The 3 electron groups require 3 orbitals, so we have 3 sp squared or sp2 hybridized orbitals. In this system, then, we take 2 of the 2p's and the 2s and mix them to get 3 sp2 orbitals, hybridized orbitals, and then we have 1 2p atomic orbital that remains unhybridized. For nitroxyl, then, for the nitrogen, the 2 half-filled sp2 orbitals participate in sigma bonds, 1 to the oxygen and 1 to the hydrogen. The lone pair on the nitrogen is in an sp squared hybridized orbital. The half-filled 2p then participates in a pi bond with the oxygen. Now we have the ammonium ion, NH4+. We know this is a tetrahedral electron group arrangement, as we saw in our last chapter. With a tetrahedral electron group arrangement, we need 4 electron groups, so we'll need 4 sp3 hybridized orbitals. And so for nitrogen, we take our 2s and all 3 of the 2p's to make the 4 sp3 hybridized orbitals. Note, however, that nitrogen is only 2s to 2p2 here. The reasoning is the formal +1 charge resides on the nitrogen atom. So the electron configuration of N+ is going to be 2s2, 2p2. Each of the sp3 electrons will interact with a 1s electron on a hydrogen atom to produce a single bond. Now we have the bisulfite anion. Monohydrogen sulfate anion has a resonance structure. Regardless of the resonance structure, around the central sulfur atom there are 4 electron groups. Therefore, it is a tetrahedral electron group arrangement. Those 4 electron groups require an sp3 hybridization around the sulfur atom. Now you notice that sulfur has an expanded valency here. There are 10 valence electrons around the sulfur. And that tells us we're bringing in d orbitals to participate in this bonding. So for the sulfur, we have sp3 hybridization. So we tend to take the 3s and the 3 3p orbitals to make 4 sp3 orbitals. But then we're going to have one of the electrons promoted up to the 3d, because that has to be involved to make the double bond. So now that we have a hybridization, we can look at the valence bond representation. The 3 half-filled sp3 orbitals participate in sigma bonds with the 3 oxygen atoms. 2 of the oxygen atoms are singly bonded, 1 is doubly bonded, and so that doubly bonded system, one of the bonds is a sigma bond. The filled sp3 hybrid orbital corresponds to the lone pair on the sulfur atom. The second bond of the oxygen double bond is due to the half-filled 3d orbital. interacting with a p orbital on the oxygen. This shows why the period's 3 to 6 elements can have more than an octet, whereas the period 2 elements cannot, because there are no available or there are no 2d orbitals that exist. Next, we'll look at iodine trifluoride. Iodine trifluoride, as we saw before, has 5 electron groups. Therefore, it is a trigonal bipyramidal electron group arrangement. In order to have 5 electron groups, we need 5 orbitals. So we have 5 sp3d hybridized orbitals. So for the iodine atom, which is a 5s2, 5p5, we mix this as follows. We take one of the Ds, 3 of the Ps, and the S to make an sp3d. And in this, we have 7 electrons. 4 of them are paired up, and then 3 are unpaired. The paired electrons are the lone pairs, and then the 3 sp3d unpaired electrons participate in a sigma bond with the 2p half-filled 2p orbital on the fluorine atoms. So now we've seen how to handle production of hybrid orbitals from our VSEPR, and then we can take the hybrid orbitals and describe the valence bonding within the system. Next, let's look at molecular orbital theory. We saw that this is a combination of orbitals to form bonds as viewed as the combination of wave functions, and the atomic wave functions combine to form molecular wave functions. Addition forms bonding MOs, and subtraction forms antibonding MOs. The bond order then is calculated by half of the difference between the bonding and the antibonding MOs. And the molecular electron configuration shows the type of MO and the number of electrons in each of the molecular orbitals. If we're going to build a molecular orbital diagram, we take the atomic orbitals, we write down their occupancy and their labels. We see how they correlate with the molecular orbitals. So we draw out our molecular orbitals in the center vertically. We fill those up with the available electrons. And then we're able to calculate a variety of properties. So let's take an example. Let's consider the lithium beryllium molecule. Not a common molecule, LIBE, but it does exist. Let's build an MO diagram for the molecule. We'll calculate the bond order for the molecule. We'll identify whether it's paramagnetic or diamagnetic. And then we will write out the molecular electron configuration for this molecule. First, let's build an MO diagram. So we'll take the 2 atomic orbitals. So lithium is a 2s1, beryllium is a 2s2. We combine these together and we end up with a sigma 2s and a sigma star 2s. We have a total of 3 electrons, 1 from lithium and 2 from beryllium, and therefore we fill them up from the bottom up. 2 go into the sigma 2s, and 1 goes into the sigma star 2s. And we use the 2s subscript to indicate that the sigma, the bonding molecular orbital, came from a 2s atomic orbital, and likewise the sigma star 2s came from a pair of 2s atomic orbitals. So bond order for this system is fairly straightforward. We take the number of sigma electrons, bottom, there's 2 of them, and then we take the number of sigma star electrons, that's at the top, and there's 1 of them. So the bond order is a half of 2 minus 1. The bond order is a half. It's a weak bond, but it is a stable system. Next Is it paramagnetic or diamagnetic? Lithium berylide is a stable molecule that has one unpaired electron. That electron in the sigma star 2s orbital, and therefore this is a paramagnetic molecule. Finally, we can write out the molecular electron configuration for this molecule using the center molecular orbitals. We first write the lower energy, the sigma 2s, so it's a sigma 2s2, and then we take the upper orbital, sigma 2s star 1. So there's 2 electrons in the bonding, 1 in the antibonding. So we have a sigma 2s2, sigma 2s star 1.